Okay, so today we're going to talk about the second derivative test as well as concavity. This is lesson 4 from unit 3. So our objective for today is that students will be able to determine intervals on which a function is concave up or concave down, identify points of inflection, and find relative extrema by using the second derivative test. Okay, so let's first look at concavity. So the first derivative test helps us to locate intervals on which a function is increasing or decreasing. That's what we did in the last section, 3.3. So in this section, 3.4, we're going to, the intervals for which f prime is increasing or decreasing will be used to determine where the function is curving up or down. So for concavity, that's our definition here. This is concavity. Let f be differentiable on an open interval I, and the graph of the function is either concave up on the interval if the derivative is increasing on that interval, or it's concave down on the interval if the derivative is decreasing on the interval. And here's an example to the right, this graph here, where we have our function 1/3 x cubed minus x, where we have concave up, downward here, and then it's going concave down. Oh, up, sorry, I said the wrong thing again. And then based on our derivative, we can find those intervals. Okay, so let's test for concavity. So to test for concavity, we have to let the function's second derivative exist on an open interval I. So if the second derivative exists, then we can define whether it's concave up or concave down. So if the second derivative is greater than 0, then the graph of f is concave up. If the second derivative is less than 0, then the graph of f is concave downward. And we'll do a test to see where it's either greater or less than 0. So let's go ahead and do an example. So the first thing we want to do when we're trying to determine whether it's concave up or down is take the second derivative. But in order to get the second derivative, we have to take the first derivative. So let's take the first derivative of this function. F of x equals 6 over x squared plus 3. I am actually going to not start with the derivative. I'm going to rewrite this so it's easier to differentiate to the -1 since I'm moving it. Okay, so then now I'm going to take the derivative, which is -6x squared plus 3 to the -2 times 2x. Okay, so we can simplify this to -12x over x squared plus 3 squared. Okay, so we got the first derivative, but we need the second derivative. So let's take the next derivative of that. So the bottom times the derivative of the top minus the top times the derivative of the bottom, which is chain rule, so x squared plus 3 times 2x. All over x squared plus 3 squared, which is 4. Okay, so this is equal to -12 x squared plus 3 squared minus, negative, that's it, so positive 48 x squared plus 3 all over x squared plus 3 to the 4th. So I'm going to take out a -12 x squared plus 3, and I have one of these here, minus 4x squared all over x squared plus 3 to the 4th. One of these can cancel and one of these can cancel. I'm going to simplify what's inside of the brackets there. So we have negative 3x squared plus 3 all over x squared plus 3 cubed. I can factor out a 3. Well, I'm going to factor out a negative 3, so that will make this 36 x squared minus 1 all over x squared plus 3 cubed. Whew. So that's f double prime of x. Okay, so there is our second derivative. Okay, so now what we need to do is we need to find where the second derivative does not exist, as well as where it is equal to 0. So where it does not exist is whatever is in the denominator. That'll tell us where it doesn't exist, and in the numerator is where it's going to be equal to 0. So let's set the numerator equal to 0 to find where that's going to be equal to 0. Well, x squared minus 1 equals 0, so x is equal to plus or minus 1. And any value will work for x in the denominator, so it doesn't matter for where it doesn't exist, because any value for x is going to work in the denominator. So our two critical points here are -1 and +1. So let's use our number line here to test these intervals. So now to test these intervals, we want to test something outside of -1, so something like -2, and see where it's going to be positive, if it's going to be positive or negative. So I don't care about the actual value you get out. I just want to make sure that you know that it's either positive or negative. So you could just simply write that here. So if I plug in -2 into my second derivative, I get a positive value. Okay, so now something between 1 and -1, 0, plug that in, I get a negative value. Something greater than 1, so if I plug in 2, I get another positive value. So where these are positive and negative, tell me whether it's concave up or concave down. So since it's positive in 2 places, that means that it's going to be concave up on those 2 intervals. So concave up on, so from -infinity to -1, and from 1 to positive infinity. And then where it's negative, it's now concave down, so at -1, 1. And so those are your intervals of concavity. Okay, let's go to our second example. So let f be a function whose second derivative exists on the open interval I. Oh, same information, just revisiting the fact of what we need to know. But let's determine the intervals on which f of x is equal to x squared plus 1 over x squared minus 4, and whether it's concave up or concave down. So again, we got to find the first derivative here. Fun with these quotients. So x squared minus 4 times 2x minus x squared plus 1 times 2x over x squared minus 4 squared. So 2x and then we can factor out 2x, and then you have x squared minus 4 minus x squared minus 1 all over, oops. Okay, so 2x times, well, these cancel out, and that becomes -5 over x squared minus 4 squared, which is equal to -10x over x squared minus 4 squared. All right, so that's the first derivative, but once again, we need the second derivative. So it's gonna be fun. Okay, so second derivative time, same thing. If you want to, I guess you could bring the denominator up and do it that way, but I'm gonna use the quotient rule. So x squared minus 4 squared times negative 10 minus negative 10x times 2 times x squared minus 4. All of this over x squared minus 4 squared to the 4th. Okay, so negative 10 x squared minus 4 squared minus, nope, plus 10 times 2 is 20, 20 times 2 is 40 x squared minus 4. We could take out negative 10 x squared minus 4 and x squared minus 4 minus 4x squared you could probably skip all the way to the second derivative if you choose. So negative 10 x squared minus 4 times that. So, oh, and I could have taken this out. Let's go back. We could delete that because I can take out one of these and one of these. I almost forgot that. So then let's move this back to 10 times negative 3x squared minus 4 all over x squared minus 4 cubed. And that's that. You can leave it like that, I guess. All right, so now we need to find our critical points. Where does it equal 0 and where does it not exist? So it does not exist at 2 and negative 2 because that's where our denominator would be 0 at. And where does this equal 0? So negative 10, negative 3x squared minus 4. So 0 equals negative 3x squared minus 4. 4 equals negative 3x squared. Negative 3/4 equals x squared. Can't take a square root of a negative number. So that's it. So there's no value that'll make that 0. Okay, so let's go and do our number line here and test our two critical points. So negative 2, 2. So if I plug in negative 3 into my second derivative, I get a positive. If I plug in 0, I get a negative. If I plug in 3, I get a positive. So concave up, we get from negative infinity to negative 2 to 2 positive infinity. Concave down, we get negative 2 to 2. Alrighty, so that is that example. so these are our points of concavity, our intervals of concavity, excuse me. So, okay, so another definition here. So let's talk about inflection points. So a point at which a graph changes concavity is called an inflection point. Note that possible points of inflection exist where the second derivative is equal to 0 or it's undefined. So we want to determine the points of inflection and discuss the concavity for this function here for an example. So it's basically what we've already been doing, right? Like we've already been finding where it does not exist or where it is equal to 0 at. So once again, the first thing we need to do is find the first derivative. So 4x cubed minus 12x squared. Find the second derivative. 12x squared minus 24x. Don't we wish they were all this easy? Okay, set it equal to 0 to find the inflection points. Let's factor out a 12x so we get x minus 2. So x can be either 0 or x can either be 2. So those are our inflection points. Now let's test them. Okay, so plug into the second derivative. We can plug in -1 and we're going to get a positive. If we plug in 1, we're going to get a negative. If we plug in a 3, we're going to get a positive value. Like I said, I don't want to see you plug in the values. I just want to see this table here, this number line. Okay, and then now you can find your concavity. So concave up from -infinity to 0 and 2 to positive infinity, and concave down from 0 to 2. Alrighty, so these are our inflection points here, right here. Inflection points. They tell us where the graph is changing concavity. All right, so that was concavity. Let's go to the second derivative test. So the second derivative test says, let f be a function such that the derivative is equal to 0, and the second derivative exists on the open interval containing c. So if f double prime of c is greater than 0, then f has a relative minimum at c f of c. If f double prime of c is less than 0, then f has a relative maximum at c f of c. So if the second derivative is greater than 0, relative min. If the second derivative is less than 0, relative max. So note, for the second derivative test, if f double prime is equal to 0, then the test fails and you must revert back to the first derivative test. Okay? So let's do an example for the second derivative. So we want to find all relative extrema for g of x equals -3x to the 5th plus 5x cubed using the second derivative test. So the first thing we want to do is, like I said, find the first derivative. We always do that. So -15x to the 4th plus 15x squared. Okay, so let's find the critical points. So the critical points are when this is equal to 0 or does not exist. So -15x to the 4th plus 15x squared. So -15x squared we could take out, so we get an x squared minus 1. So we have x can either be equal to 0 or positive -1. Okay, so then these are our critical points points. Forgot what I was writing. F double prime of x now, so let's find the second derivative. So we get negative 60x cubed plus 30x. So now we want to use the critical numbers from the first derivative to find the relative min and relative max. Okay, so we're going to use these points and plug them in. So f double prime of 0 is equal to 0. F double prime of negative 1 is 60 minus 30, so 30. And f double prime of positive 1 is negative 60 plus 30, so negative 30. Okay. So since f double prime of 0 is equal to 0, we know the test fails at 0. So we have to revert back to the first derivative test and see if it is going to be an inflection point or not. So let's test 0. So if I plug in negative a half, we want to use a half because we're already using negative 1. We know negative 1 and positive 1 are critical points, so we want to use something between that. So is negative 1/2, when I plug it in, positive or negative? Well, if I plug it in, I'm going to get a positive. And if I plug a positive 1/2 in, I also get a positive 1/2. Like I said, we have to plug in a half because our critical points are at negative 1 and positive 1. So we can't plug those in, or we're just going to get 0. So since 0 is positive on either side, it's not changing direction. It's still positive. It's still increasing. So it's neither a max or a min. But this value here, negative 1, is our relative minimum. And this is a relative maximum. Okay? And this is going to be at negative 1, negative 2, and this is at 1, 2. So to find the y value, I took 1 and negative 1 and plugged it back into the function to get where our relative min and our relative max are at. I would like to see you guys put the points where the min and the max are actually at, not just the x value. I would like to see the y value as well. So to do that, like I said, I just plugged it back into the original function. So g of 2, not 2, sorry. G of 1 is equal to negative 3 plus 5, which is 2. And g of negative 1 is equal to 3 minus 5, which is negative 2. Okay, so that's all I did to get those. All right. Oops, looks like I didn't need this extra page. Okay, so let's classify all the relative extrema for g of x equals 3x cubed minus 18x plus 1 using the second derivative test. Okay, so once again, we need to find the first derivative and its critical points. So the first derivative is 9x squared minus 18. And the critical points here, so when it's equal to 0, we're going to factor out a 9, so that would be 2. So we get x squared minus 2, 2 equals x squared, square root, so x equals a plus or minus square root of 2. Okay, so that's our critical values. So then now we want to find the second derivative, which is 18x. And so we're going to plug that in to, oh sorry, I called these all f of x. They're supposed to be g of x. G of x, g of x. And now we want to plug in the square root of 2 and plug in the negative square root of 2 and see what we get. So do we get a positive? Do we get a negative value? Okay, so when we plug in this one, we get a positive. When we plug in this one, we get a negative. So we have a relative min here at x equals the square root of 2, and here we have a relative max at x equals negative square root 2. Okay, and that is it for concavity.